What if I told you that this very human experience is a pale shadow of a fundamental law of the universe, a law we are just now learning to command? In 2019, a single machine, humming in the coldest, quietest place on Earth, did something that defied the logic of our entire digital civilization. It solved a problem in 200 seconds that our mightiest supercomputers, titans of calculation that predict weather and map the cosmos, would need 10,000 years to even attempt. This wasn't just an upgrade. It was a whisper from a different reality. A whisper that suggests the world as we know it, our science, our economy, our very understanding of what's possible, is built on an incomplete operating system. Today, we're not just talking about faster computers. We're talking about a paradigm shift so profound it rivals the discovery of fire or the invention of the wheel. We're going on a journey to the quantum frontier to understand the ghost in the machine that promises to rewrite the future. The question is, are you ready to meet it? Our story, like all great revolutions, begins not with a bang, but with a question. It was 1982, and the brilliant, eccentric physicist Richard Feynman stood before an audience. He wasn't just a Nobel laureate. He was a master storyteller of the cosmos, a man who saw the universe as a grand, intricate puzzle. And he had identified a colossal problem. For decades, we have been building classical computers marvels of engineering that run on a simple, binary language of O south and 1 south. On or off, yes or no, true or false. This logic built our modern world, from the phone in your pocket to the International Space Station. But Feynman knew this was a lie. A convenient, useful lie, but a lie nonetheless. The real world, the universe at its most fundamental level, doesn't speak in O south and 1 south. It speaks in maybes, in probabilities, in paradoxes. The world of quantum mechanics, which governs the dance of atoms and the chemistry of life, is a bizarre, counterintuitive realm. An electron isn't just here or there. It can be in a haze of all possible locations at once. This is the principle of superposition. Imagine you spin a coin. While it's in the air, spinning, is it heads or tails? In a way, it's both and neither. It's in a state of potential. Only when it lands, when you measure it, does it resolve to a definite state of heads or tails. A quantum bit or qubit is like that spinning coin. It can be a 0, a 1, or a shimmering probabilistic blend of both simultaneously. Now imagine you have 2 such coins, magically linked. If you know one landed on heads, you instantly know the other is tails, no matter how far apart they are. This spooky connection is entanglement. Feynman's radical idea was this. Why are we trying to describe this rich, complex, spinning coin reality with a language that only knows heads or tails? He said it's like trying to paint the Mona Lisa with a single black crayon. You can approximate it, sure. You can spend an eternity drawing dots to hint at the shades and colors, but you'll never capture the true essence, the subtle smile. He proposed building a new kind of computer, one that operates on these quantum principles. A computer that doesn't just approximate the universe, but mimics it. A machine that speaks the universe's native tongue. This wasn't just a call for better hardware. It was a philosophical challenge. It implied that to truly understand reality, we had to build a piece of it. A machine that could simulate how a drug molecule truly behaves, not just how our best guess says it should. A machine that could unravel the quantum secrets of photosynthesis or design materials that conduct electricity with zero resistance. The possibilities were intoxicating, but the path to building such a machine was shrouded in darkness. It would take a generation of pioneers to even begin to find the way. Feynman planted the seed, but for it to grow, engineers and physicists had to venture into a realm of unprecedented difficulty. Building a quantum computer is not like assembling a PC. It's more like trying to build a perfect, intricate sandcastle during a tidal wave. The very properties that make qubits so powerful, superposition and entanglement, also make them catastrophically fragile. A qubit is a ghost. It exists in a delicate, probabilistic state that can be destroyed by the slightest disturbance. A stray vibration, a tiny fluctuation in temperature, a passing magnetic field, or even a cosmic ray from a distant exploding star can cause it to decohere, to collapse from its rich quantum state into a mundane, classical 0 or 1. The calculation is ruined, the magic gone. To protect these quantum ghosts, scientists had to build the most extreme environments on Earth. Picture a laboratory that looks like a sci-fi movie set. In the center is a massive, chandelier-like structure of gleaming gold and copper wires, a cryostat plunging down into a series of nested chambers. This isn't for show. This entire apparatus is a refrigerator of unimaginable power, cooling the quantum processor at its core to temperatures as low as 50 millikelvin. That is colder than the blackness of deep space. At this temperature, atoms nearly stop vibrating, creating a quantum silence where the qubits can think without being disturbed. These processors are then shielded in lead-lined rooms, isolated from the Earth's magnetic field, and protected by vacuum chambers that make a bank vault look like a cardboard box. The engineers working on them are part of a silent, patient tribe, celebrating victories measured in microseconds, extending the coherence time, the length of time a qubit can hold its quantum state, from 10 microseconds to 20 was a monumental achievement. Adding just one more stable qubit to a processor was cause for a champagne toast. It was during this long, arduous period in the 1990s and 2000s that the theoretical stakes were raised even higher. In 1994, a mathematician at Bell Labs named Peter Shor dropped a bombshell. He devised an Shor's algorithm that proved, on paper, that a functional quantum computer could crack the encryption that protects virtually our entire digital world. The security of your bank account, government secrets, corporate data, it all relies on the fact that classical computers find it impossibly hard to factor very large numbers into their prime components. Shor's algorithm could do it exponentially faster. Suddenly, the race to build a quantum computer wasn't just a scientific curiosity. It was a matter of global security. The question hanging in the air of every lab was no longer if they could build one, but who would build a powerful one first. For decades, the answer to when will a quantum computer do something a classical computer can't was always in the future. Then in the fall of 2019, the future arrived. Google published a paper in the journal Nature with a bold, electrifying claim. They had achieved quantum supremacy. Their 53-qubit processor, named Sycamore, had performed a specific, esoteric task in 200 seconds. Google's team calculated that the same task would take Summit, then the world's most powerful classical supercomputer, an astonishing 10,000 years to complete. The world of tech held its collective breath. So, what was this Herculean task? It wasn't cracking codes or designing drugs. It was a carefully designed mathematical problem called random circuit sampling. Imagine you have a complex maze with millions of paths, and at each fork, the path you take is determined by a quantum roll of the dice. A classical computer would have to calculate every single possible path, one by one, to figure out the final probability distribution of where you might end up. It's a brute force nightmare. Google Sycamore, however, could essentially explore all the paths at once, thanks to superposition and entanglement. It ran the quantum maze and came back with a snapshot of the outcome, a feat of parallel computation that was, in that moment, beyond classical reach. This was the Wright brothers' moment at Kitty Hawk. Their first flight lasted only 12 seconds and covered just 120 feet. It didn't carry any passengers or cargo. It didn't solve the world's transportation problems. But it did one crucial thing. It proved that powered flight was possible. It silenced the skeptics and opened the door to the sky. Of course, the story got more complicated. IBM, Google's main rival, quickly published a counter-argument. They claimed that with better classical algorithms and access to a supercomputer's massive hard drive, they could solve the same problem in 2.5 days, not 10,000 years. the debate over the term supremacy began. Was it truly a final, unassailable victory, or just a temporary lead on a very specific racetrack? In the end, the exact numbers didn't matter. The psychological barrier had been broken. A quantum computer had done something measurably faster than any classical machine. It was proof of concept. The sandcastle had held against the tide, if only for a moment. The age of theoretical quantum computing was over. The age of experimental, noisy, but functional quantum computing had begun. The next question was no longer can it fly, but where will it take us? The flash of quantum supremacy was exhilarating, but it was just a flashy demo. The real revolution won't be about solving abstract math problems. It will be about solving human problems. This is the shift from quantum supremacy to quantum advantage, the point where a quantum computer solves a practical, valuable, real-world problem faster, cheaper, or better than any classical computer ever could. This is where the story moves from the lab into our lives. Consider the pharmaceutical industry. Today, discovering a new drug is a process of painstaking, expensive trial and error. Scientists might test thousands of chemical compounds to see if one has the desired effect on a virus or a cancer cell. It can take over a decade and cost billions of dollars. Why? Because molecules are quantum systems, and classical computers can only guess at their complex interactions. In 2020, Google's team used Sycamore to perform the first ever chemically accurate simulation of a small molecule, diazine. While a classical computer could also do this, it was a crucial stepping stone. Imagine a future where a pharmaceutical company can model a complex protein from a novel virus on a quantum computer. They could then simulate thousands of potential drug molecules interacting with it, observing at a quantum level which one binds perfectly to disable the virus. They could design a life-saving drug with atomic precision in months, not years. This is the dream, turning drug discovery from a game of chance into an act of design. Or think about the backbone of our global economy, logistics. Every day, companies like Amazon, FedEx, and UPS face a modern version of the traveling salesman problem. What is the most efficient route for a fleet of thousands of vehicles to make millions of deliveries? The number of possible routes grows exponentially, quickly overwhelming even the best supercomputers. In 2022, researchers used a quantum computer to tackle a version of this vehicle routing problem. For small-scale tests, it performed as well as classical methods. But the potential it showed for larger problems was immense. Quantum advantage here could mean a delivery company saving millions of gallons of fuel, drastically cutting carbon emissions, reducing traffic congestion in our cities, and getting you your package faster. And then there's the burgeoning field of quantum machine learning. In 2023, a quantum neural network was shown to identify patterns in datasets that were invisible to classical AI. Think about what this could mean for medicine. A quantum-powered AI could analyze an MRI or CT scan and detect the subtle, ghostly signature of cancer cells long before a human radiologist could see them. In finance, it could analyze market data and spot the faint, chaotic signals that precede a market crash, giving us a chance to react. These early experiments are the first notes of a symphony we can't yet hear in its entirety, but we know it's going to be transformative. The path to this incredible future is not a straight paved highway. It's a treacherous mountain trail guarded by 3 formidable dragons: errors, security, and a scarcity of talent. The first and most fearsome dragon is errors. Today's quantum computers are noisy intermediate-scale quantum, NISQ devices. Noisy is the key word. As we discussed, qubits are fragile. Errors constantly creep into the calculations, corrupting the results. To run powerful programs like Schur's algorithm, we need fault-tolerant quantum computing. The solution is a concept called quantum error correction, which is mind-bendingly complex. It involves using many physical qubits, perhaps thousands, to form a single stable error-corrected logical qubit. In 2024, we saw incredible progress in this area. But we're still a long way from the millions of stable logical qubits needed to topple our current digital infrastructure. This brings us to the second dragon, security. Shir's algorithm is a ticking time bomb at the heart of our digital world. The moment a large-scale, fault-tolerant quantum computer exists, the RSA and ECC encryption standards that protect everything from your WhatsApp messages to nuclear launch codes will be rendered obsolete. They can be broken. This has sparked a frantic, global race to develop post-quantum cryptography, PQC, new encryption methods that are resistant to attacks from both classical and quantum computers. In 2022, the U.S. National Institute of Standards and Technology, NIST, announced its first set of standardized PQC algorithms. But now comes the monumental task of upgrading the entire world's digital infrastructure. It's like trying to rebuild the foundation of every single building in a city, all at once, while people are still living in them. The third dragon is a human one, the talent gap. Quantum computing is a field that demands a rare blend of expertise in quantum physics, advanced mathematics, computer science, and engineering. The world needs a new generation of quantum engineers, programmers, and technicians, but our education systems are only just beginning to catch up. The demand for these skills already far outstrips the supply. We have the blueprints for a starship, but we have a critical shortage of people who know how to build the engines, navigate the cosmos, or even read the maps. Bridging this gap is as critical as any hardware breakthrough. So where does this leave us? The consensus is that practical, widespread quantum advantage is not a matter of if, but when. Some experts predict 5 to 10 years for specific optimization problems. Others say 15 to 20 years for more complex applications. The trajectory is undeniable. In the interim, the most promising path forward is hybrid quantum classical computing. It's the best of both worlds. Let a classical supercomputer handle the bulk of a problem, but offload the impossibly complex quantum portion like simulating a specific molecular interaction to a quantum processor. It's like having a race car engine inside your family sedan, ready to be fired up for the one stretch of road where you need impossible speed. By 2035, some analysts project the market for quantum computing could be worth over $800 billion, disrupting finance, energy, pharmaceuticals, and manufacturing. We envision a future with hyper-efficient batteries designed at the quantum level, new materials that make carbon capture a reality, and an eye that can finally tackle humanity's grand challenges, like modeling climate change with perfect fidelity, or even helping us understand the origins of the universe. But the most profound impact of quantum computing may be something we cannot yet foresee. The creators of the first classical computers in the 1940s envisioned them as tools for calculating artillery tables. They could never have dreamed of the internet, social media, smartphones, or artificial intelligence. They gave us a new tool, and human ingenuity did the rest. Quantum computing is not just a better tool. It's a fundamentally different kind of tool. It offers us a new way to think, a new lens through which to see the universe. What questions will we ask when we have a machine that can think in the language of reality itself? The story of quantum computing is more than just a tale of technology. It's a profound lesson in the power of human curiosity and persistence. It began with Feynman's audacious dream, a challenge to think beyond the limits of our own logic. It was carried forward by thousands of scientists and engineers who toiled for decades in the face of immense skepticism and failure, celebrating victories measured in fractions of a second. It teaches us that the greatest leaps forward don't come from following a map, but from daring to explore the blank spaces where the map ends. So, what is the lesson for us, here and now? It's that we are all standing at the dawn of a new age, and we have a choice. We can be intimidated by the complexity, or we can be inspired by the possibility. You don't need a PhD in physics to be a part of this revolution. The lesson is to cultivate a quantum mindset in your own life. Embrace paradox. Be comfortable with uncertainty. Understand that the most interesting answers often come from asking the weirdest questions. Stay curious. Read a book, watch a documentary, or take a free online course about the basics of quantum computing. Advocate for STEM education in your community so we can close that talent gap and empower the next generation of pioneers. The future is not something that happens to us. It is something we build together. The quantum revolution is coming, and it needs artists, ethicists, writers, and dreamers just as much as it needs scientists. What part of this quantum future excites you the most? Is it the potential to cure diseases, to solve our climate crisis, or something else entirely? How do you think this technology might change your industry, or even your daily life in the next 20 years? Share your thoughts in the comments below. Let's build a community of curious minds. If this journey to the edge of reality sparked your imagination, please hit that subscribe button to join us for more stories on the frontiers of science and technology.